Dear students, welcome to the second lecture of Open Channel Flow. In this lecture, we will discuss some basic aspects of Open Channel Flow. Let's start discussing on velocity distribution in Open Channel Flows. Um, Velocity distribution, speaking realistically in Open Channel Flows, is three-dimensional in nature due to the existence of turns and bends and arbitrary shape of the boundaries and different corners and the bed roughness. The velocity becomes three-dimensional in nature, but the longitudinal component of the velocity, as you can imagine, is the dominant component, and and as engineers, rather than focusing on the three-dimensional nature of the open channel flows, we often focus only on the longitudinal component. Uh, in the diagram on the right hand side, you can see some the velocity distribution in some open channels of different shapes: rectangular, trapezoidal, triangular, and circular. In these diagrams, you can see there are different contours of velocity on the cross sections. These contours of velocity are known as the isovels. The isovels are the equal velocity contours on the cross section, and studying the isovels, you can see that the velocity varies from zero at the boundaries to the maximum at the nearer at the center of the channel. So along with the velocity contours or the isovels, uh, on the right hand side we can see the vertical profile of the velocity of the longitudinal velocity, the vertical profile. uh, you can see that the vertical profile gives you the variation of the longitudinal component of the velocity along the y direction or the vertical direction. Let's talk about the vertical velocity profile more. In the diagram on your right hand side, you can see that you can see a typical velocity profile of the longitudinal component. The profile which is shown here can be expressed by a power law or a logarithmic law mathematically. So the velocity varies from zero at the boundaries to the maximum at some distance below the surface. So this is a typical phenomena of the open channel flow, that the maximum velocity occurs not at the surface uh, practically, but some distance below it. This phenomenon is known as the velocity dip. The velocity dip is caused by some secondary currents in the channel, as we mentioned before, that along with the primary longitudinal currents or flux of flow, there are certain lateral or normal fluxes or secondary currents which causes this velocity dip. Also note that velocity dip has nothing to do with the wind shear at the surface, which perhaps you can imagine. Uh, it is nothing to do with the wind shear. Velocity dip also is a function of the aspect ratio of the channel. Aspect ratio is the depth to width ratio of the open channel. So the velocity dip is higher for narrow deep channels than shallow wide open channels. So as we mentioned before, that the longitudinal component is the dominant component which we often focus on. Moreover, engineers actually focus more on the depth average mean velocity of in the longitudinal direction. So the actual longitudinal velocity, which is given by small v here, is a function of the depth, or is a function of y here, as it is shown here. Let's talk about the momentum correction factor. Uh, so the momentum is a vector quantity, of course, and momentum can be estimated by using the depth average velocity, capital V, or we can estimate the momentum of flow by taking into account the depth variation of the velocity, uh, and integrate that over the whole cross section to arrive at the momentum of flow. So you can imagine that if we estimate momentum by the depth average velocity, capital V, so there will be an error in the estimation of the momentum, and that error has to be corrected by using the momentum correction factor, which here is given by the Greek alphabet beta. Beta is of course the ratio of the actual momentum which is estimated by the depth varying velocity component small v by the momentum estimated using the depth average mean velocity, capital V. Here you can see that the numerator gives you the momentum which is the correct momentum of flow, which is estimated using small v, and the denominator here gives you the momentum which is estimated by using mean velocity, capital V. What we saw in the what we discussed in the previous slide, that if we don't have a power law or a logarithmic law to express the velocity distribution, we have the velocity measured over discrete points over a cross section, then the integration here in that ratio has to be substituted by a summation, and in that case the momentum correction factor is given as summation of small v square into delta A by capital A into capital V square. Like the momentum correction factor, the kinetic energy correction factor can also gives you the same, by the same concept, the kinetic energy correction factor can be defined. If we estimate the kinetic energy by using the mean velocity, capital V, that gives you an error. So that error has to be corrected using a correction factor which is called the kinetic energy correction factor, and which is given by the Greek alphabet alpha. Alpha is the ratio of the actual momentum calculated using the depth varying velocity small v by the kinetic energy computed by using the mean velocity, capital V. So you can see that alpha is given by integration of small v cube into dA integrated over capital A by capital A into v cube. Note that again, like the previous slide, if you don't have that the actual velocity distribution, what you have is the velocity estimated over some discrete points over the cross section. Then the kinetic energy correction factor is given as alpha is equal to summation of small v cube into delta A by capital A into capital V cube. So That is all for the time being. We will be discussing more on different aspects of open channel flow in the next lecture, where we will start discussing on the important conservation equations of open channel flow. Thank you very much.